Hello and welcome, everyone. My name is Lauren Herrington, and it is my privilege to be the host of today's webinar. Joining me, we have three leaders of the AAVSO's various sections. They'll be giving some presentations on their section's activities later today. But before we get to that, I do have a few quick housekeeping announcements to make. First, I'd just like to offer a reminder for those of you who don't use Zoom too frequently, kind of like me. At the bottom of your screen in Zoom, you should see a toolbar with a few options available. There's the chat box where we've all just been introducing ourselves, but there's also a feature which is specific to Zoom Webinar. That is the Q&A box. When you click on that box, you will have the option to type in a question for any of our presenters, and I highly recommend that you do just that. Today, Arne will be answering questions immediately after his presentation, and Walt and Eric will be tag teaming to answer questions towards the end of the webinar. When you submit a question, please remember to address your question to the specific section leader who you're wanting to ask. We'll do our best to get to all of your questions before the webinar is over. One more setting I'd like to point out before we move on. You do see a button labeled CC or Show Captions that can be useful to enable or disable Zoom's automatic closed captioning. I'd also like to give a quick shout out to our ongoing mini-series, of which this webinar is a part. This is the Sections in the Spotlight mini-series, in which we are hearing from representatives from every single one of the AAVSO sections or special interest groups. Today, we'll be hearing from the AAVSOnet Section, the Cataclysmic Variables Section, and the Short Period Pulsators Section. While next week, we'll be hearing from the Spectroscopy Section, the High Energy Network Section, and the Photoelectric Photometry Section. If you're interested in any of those last three topics, which I just mentioned, you can go ahead and pre-register for next week's webinar by visiting our website at aavso.org/webinars. I hope to see you there. And now, a special announcement for which the photograph is not loading. You might have to imagine a very dramatic rocket right there. So, we are having our annual meeting, our 113th annual meeting, at the U.S. Space and Rocket Center in Huntsville, Alabama. And trust me when I say they have some pretty impressive rockets there. The opening reception will be held in this giant hall that has a Saturn V rocket mounted in it. Can't wait for that. And our Arlo Landolt lecture will be presented by Dr. Bradley E. Schaefer, who I believe is in attendance here today. Hello, Dr. Schaefer. Thank you for being here. Of course, we'll have 2 full days of presentations and posters and a banquet to cap things off. And it promises to be possibly the best annual meeting that any of us will be able to remember. So I hope to see you there at the annual meeting in Huntsville, Alabama this November. For more information about the meeting and to get information on registration, please visit our website at aavso.org/113, our 113th anniversary. Oh, there's the image. Well, convenient time for it to load. All right. Now, I would like to thank our 2024 series sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. All right, now, before we move on to the individual section presentations, I would like to offer a bit of context about the AAVSO and its section system for those of you who might not be familiar. So we'll start with the AAVSO. To those of you who are new to the organization, our acronym stands for the American Association of Variable Star Observers, and our mission is to enable anyone, anywhere to participate in scientific discovery through variable star astronomy. Now, that is a broad and ambitious mission, and there's a few different ways that we accomplish that. Before we get to that, I'd like to introduce you to AAVSO members. So the AAVSO is a very large organization composed of observers who go out and collect data, as well as analysts who do what that sounds like and analyze data. We have people of all expertise levels. So we have those who are just starting out and have only just heard what a variable star is and they're interested in learning more. We also have people who have been doing this for 60 years and who are looking to teach others and share their knowledge. There's one thing that unites all of us, and that is that we all enjoy doing science with the sky. Our observers are equipped with a wide variety of tools. Some people choose to simply use their eyes, whether that's using just the naked eye, walking outside, looking up in the sky, studying the brightest variable stars, or by using telescopes, or by using binoculars. We have people who use cameras and advanced detector devices and the very large observatory, meter class telescopes, and people who do whatever they can to contribute with what is on hand, such as AAAVSO here, who built his own solar telescope so that he could contribute to sunspot counts. And I won't go through all of these, but I do want to highlight a few key numbers about the AAVSO to give you a sense of scale and what we do. We do have about 1,200 members at any given point in time. In addition, we have 800 observers and 200 volunteers. You do not have to be a member of the AAVSO in order to be involved. Many of our observers and volunteers are not actually members. We're a relatively small organization with 6 staff and 3 contractors. Our budget's about $1 million a year. We do a lot with that money. Some of the programs that we have include the webinar series in which you're currently watching. We also run educational choice courses and write manuals and offer a mentorship program, lots of different ways to educate yourself about variable stars. Our data is used in about 400 publications per year, so we're having a large impact on science, to say the least. And this data comes from a selection of databases tracking photometry, spectroscopy, sunspot counts, transits of exoplanets, and also the variable star index, which keeps track of all of the variable stars that we know about pretty much that are relevant to study. And of course, we have the meetings such as the one coming up in Huntsville, Alabama, which I mentioned, and workshops that sometimes go along with that. So coming back to our lofty mission, there are several different ways that we achieve this mission. Collaboration with professionals, partnerships with organizations such as the SNOOS project, which is currently ongoing, educational activities, taking care of our databases. One of the key ways in which we do these things, in which we achieve our mission, is the section program. So when I first joined the AAVSO, I heard about these sections and I really wasn't sure what to think. What is a section? Like, that's a broad term. It took me a couple months to get a straight answer, honestly, but I'll go ahead and give it to you right now. A section is a special interest group. If you have ever been in a club that had a special interest group, this is exactly the same sort of same sort of definition. So an AAVSO section is a group of people who are united by a relatively niche interest and who study a particular class of objects or who use a particular mode of observing. They get together to develop tools, to share techniques, to share observations, to perform analysis together. Whatever their choice of activity is, they are all united by their passion for this single subject. We have 12 subjects, 12 interest groups, which currently have ongoing sections, including today's presenters, who will be talking about the AAVSOnet section, our remote telescope network, the Cataclysmic Variables section, which studies cataclysmic variables, and the Short Period Pulsator section, which studies short period pulsating stars. Sections are structured so that they have a leadership team as well as a set of members. The section leadership team includes both the leaders who plan the activities, the meetings, and also science advisors who help the section find useful scientific projects to work on. Now, I'd like to focus on the participants because that's what I'm hoping that all of you in the audience will become today. To participate in a section, it's very, very simple. There's two ways that you can become engaged. If you visit our website at aavso.org/join-a-section, you'll find instructions for joining that section's forum on our website. This is a good way to preliminarily become involved in a section and stay up to date with what's going on. Section leaders visit their forums and post regular updates on what sort of activities are available. Also, if you're interested in becoming engaged more in depth in participating in projects and collaborating on papers and stuff like that, I highly encourage you to reach out directly to the leader of the section that you're interested in. You can do this by going to our website, aavso.org/observing-sections. This will get you to the main list of sections which are available. Click on the one which you're interested in. At the very top will be the names of the leaders of the section, and next to that, a link to contact them. Just click on that contact link, send them an email, express your interest, and they will involve you. It's very simple. All right. And with that, I would like to hand things over to our first honored section leader of today, and that is Arne Henden, who will be presenting on the AAVSOnet section. Arne, please take it away.
Okay, thank you, Lauren. And welcome to everybody from sunny California, where I'm at the SAS meeting. Today, I'd like to talk a little bit about the AAVSOnet section. And so let me go ahead and share screen and start a presentation here. And so the AAVSOnet section is a little different than some of the other sections in that it not only does the usual bringing together of people who have like interests in robotic telescopes and helping to run them and also using them, but it is also the AAVSO's remote telescope facility, and so it's available to anyone who is a member of the AAVSO. So the AAVSOnet itself is this collection of telescopes. It's been up and running for over a decade now. 2006 was the first telescope, and it generates something in the order of 15,000 images per month across the telescopes that are in the network, and there's been well over 3 million images that have been taken to date. The facility is not run by the staff of the AAVSO. It's run by volunteers, people like you, for the benefit of other AAVSO members. Something in the order of 60 users per quarter have proposed to look at certain objects and have gotten data from those. And so it's subscribed nicely, but it's not oversubscribed. So if you have objects that you want to look at, you can certainly propose, and in most cases we'll get time. The AAVSOnet is a full sky coverage network. We have sites in the northern and in the southern hemisphere. And instead of you accessing the telescopes directly and controlling the telescopes, it is a queue-scheduled system. The images are taken for you. They are run through an image pipeline that calibrates the images, dark subtracts, and flat fields. And then those are automatically sent to you either through an anonymous FTP site or to the AAVSO's VPHOT photometric analysis program. Here are some of the sites for AAVSOnet. We have a telescope in my backyard, BSM, New Hampshire. There's a bunch of them down in the southwestern part of the US, and there are 3 telescopes currently in the southern hemisphere, in New Zealand, and 2 places in Australia. The telescopes are broken into basically 2 types. There are some that are what we call bright star monitors because they are smaller aperture telescopes, mostly the Takahashi E180s, 7-inch astrographs that will go as bright as sort of 3rd magnitude, and then we'll go all the way down to 14th magnitude, usually with at least 4 filters that you can use. In many cases, such as the one in my backyard, there are specialty filters that can be requested. These have a field of view of about 1.5 square degrees. So they actually do cover a pretty good area of the sky so that you can pick up comparison stars. And they are not inexpensive systems. If you went out and bought an equivalent system, it would be about $40,000 per installation. So it's a good way of being able to use equipment that you might not be able to afford. There are also 3 what we call faint star monitors. These are bigger telescopes, sort of in the half-meter class. They can go fainter. There are both northern and southern telescopes. We have 3 of those now. There's a 4th one. Walt Cooney is part of the 4th one that we're looking for a home for that telescope, a site for it to be set up at. This is one of the typical bright star monitors. This one is in Hawaii. It's, like I said, a Takahashi E180 on a Paramount. And they're compact, nice systems. They often are put in backyards of observers, but can also be hosted at other sites such as schools and colleges. This is one of the larger telescopes. This one, Walt Cooney is a partner of. This is MPO 61, where the 61 refers to the 61 centimeter size of the telescope, located in the hill country of Texas. And then here are some of the light curves of data that have been acquired by observers such as yourself of 7 long period variables. These plots were actually made by Lauren, so thank you very much. And they are from Frank Shore, who is a longtime observer with AAVSOnet. So you can see the data quality is actually pretty high that comes off of these telescopes. You can also do very precise measurements, such as this one with a transiting exoplanet. So these telescopes are very capable. So why would you use AAVSOnet? You may be living in a urban environment, such as downtown Boston or wherever where you have bright skies and it's difficult for you to do your own observations. You may be living in an apartment where you don't have space for your own telescope. And so in order to use it, you would have to go out of your city. And this is just a convenient way of doing it from your armchair. There may be interesting objects that you can't see, a southern hemisphere target from your northern hemisphere house. And as I said, the setups are professional quality, expensive equipment, well maintained. And one of the problems with robotic telescopes is that they usually require technical skills in order to put together your own system. Somebody else has done that for you. And you may just want to learn how to do photometry with a digital detector. And in some cases, we have spectrographs so that you can do spectroscopy. So as I said, it's a membership benefit. So all you have to do is be an AAVSO member. There's no hourly fee or anything, but what you have to do is submit a proposal stating what object you want to look at and why you want to observe it. And what you'll get back are calibrated images. So here's the proposal form itself. Very simple. You notice a box there that all you have to do is fill in the reason why you want to observe a particular object. Most cases, the observations are scheduled by a telescope allocation committee who reviews the proposal, and we would like you to tell us why you want to observe the object. It helps us a lot in deciding whether or not the observation is actually feasible with the network equipment. So the section itself is actually what I would call pieces of other sections. It's both an observing section, it's an instrumentation section. You can get involved in setting up these systems or maintaining them. And then there's lots and lots of software and analysis of data that is involved with AAVSOnet as well. We do have a forum that's available for asking questions, either about AAVSOnet or other robotic systems, and perhaps you can give us suggestions as for improving the network. And we have plenty of volunteer positions for hosting systems, looking at the images, doing some of the software and things like that, or just observe with the equipment. So if you want to volunteer, you can host a system. We have a couple systems such as a half-meter class telescope, which needs a location. You can maintain the equipment. There are 9 different sites, and unfortunately, they don't all operate every night. And part of that is because they may have a problem that's specific to that particular site, and somebody needs to diagnose and help out. And then in some cases, there's a host for the site for the telescope, but external people to actually do the operations. So you can operate such a system. And that would be such things as looking at the weather conditions, and if it's clear, go ahead and open up at sunset, make sure that all things like flats are taken, darks are taken, and look at the image reviews that come down to make sure that there isn't some failure that's starting up some image defect or something, or the temperature is rising on the thermoelectric cooler, and those failures are nice to pick up at the very beginning. So for each telescope, there's an image inspector, somebody who actually looks at the images that are coming down and looking for problems, and then telling the administrators for the facility, for the network, if a problem exists. And the network administrators, there's currently 4 of them. Cliff Kotnick is involved, George Silvas, Ken Menzies, and myself. There are things like writing the software for the pipeline, getting these new systems configured. There's a fair amount of software on the desktop that needs to be maintained and things of this nature. And so we're always interested in getting more people involved in the network and helping out on this stuff. So the current status, there are 1, 2, 3, 4 of the BSMs are working reasonably well. There are 2 BSMs that have some problems and need some work. The one in Hawaii, for example, needs commissioning after replacement of a board in the mount, and finding somebody in Hawaii who's willing to, this is on the Big Island, is willing to stop in and help out for a couple days, turns out to be kind of a problem. The New Zealand Large Telescope is currently down for reluminizing the mirror. But we're hoping that will come up fairly shortly. And then 2 of the other 24-inch class telescopes are working just fine. So here's some contact information. You can just post to the forum if you have questions. You can also send to 3 specific email addresses if you need to get more personalized attention on something. And then on the web itself, the main AAVSO webpage for joining the AAVSO, and then the specific webpage for the AAVSOnet section. And then finally, this is a volunteer network, but it's also a network that for a large part has been donated by various vendors. And we are certainly appreciative of all the work that people have put into it, and all the hardware and software that has been given to the AAVSO in order to make this facility something that actually is usable. So with that, I'll end and open it up for questions.
Excellent. Thank you so much, Arne. So I think our first question here is actually about AAVSOnet's spectroscopic capabilities. Can you talk some more about that?
Yes, we have 2 ways of doing spectroscopy right now with AAVSOnet. The main one, of course, is we have a couple of the SA200 diffraction gratings that are in one northern telescope, one southern telescope. And these will just give you low resolution spectra, but it's an entryway into looking at stellar spectra. We then have an E-shell spectrograph that's on the New Zealand telescope. This gives you an RF 12,000-ish view of very bright stars. That facility is still undergoing commissioning, as a matter of fact. I'm about ready to send down a new CCD camera, well, CMOS camera, for that instrument, and we're hoping that that will come online sometime this northern summer. And that one, we have a group of amateurs that are down in the New Zealand area who are going to be helping us get that up and going. But those are the main things we have right now for doing spectroscopy with AAVSOnet.
Excellent. Okay, thank you. As a follow-on to that, we have a question from Margaret Miller who asks which wavelength regimes you can study with the spectroscopic equipment that AAVSOnet has available.
With the eShell spectrograph, it goes from about 400 to 700 nanometers. The diffraction gratings are pretty much the same range, just, RF50-ish instead of an RF 12,000. So very low resolution work.
Got it. Thank you. Okay, next question here comes from Wayne Buck, who asks if AAVSOnet has any collaborations with professional researchers in order to support any of the work that you're doing. Is that something the section engages in?
That one I don't quite understand. I mean, we actually have professionals who are using the facility. There are a number of member observers who look at the postings for campaigns, the alert notices, and then have proposed for observing those specific objects. And so that data then is taken by the specific AVSO member, but then goes to the researcher who's asking for that data.
Got it. Thank you. And a clarification from Wayne is that he did mean to support the researchers' projects. So I think that answered the question well. Okay, our next question here comes from Paula Scutis, who, by the way, just gave an excellent webinar a couple of months ago. Paula asks if any of the FS ones, the faint star ones, have frame transfer CCDs with no dead time or binning capability to minimize the dead time between exposures.
All of the faint star monitors have CMOS cameras, and so you can take extremely short exposures. The limitation is actually in the acquisition software. We use MaximDL for acquiring the images, and there's probably about 4 seconds of dead time between each image. There are ways in which you could probably support faster operations. You can do windowing of the CMOS cameras and use different software as opposed to MaximDL. That would be on a specific project by project basis, but I think you could probably get down into sort of the 1 hertz level. I don't know if you can go much faster than that. So it's probably not as good as what Paula is looking for, but you can do relatively fast cadence on these systems.
Great. Okay, thank you. Quick reminder before the next question, because I think I see a couple questions in the chat. If you could post them in a Q&A box, we'll be able to get to them faster. So not the chat box in Zoom, but the Q&A box. All right, so our next question here comes from Vincent Boutard, who asks if there's any plan to have AAVSOnet telescopes in Europe.
Good question. I'm a partner of a telescope that's in Spain. And I've been thinking about giving away my part of the telescope time for AAVSOnet. But it would be nice to have an actual AAVSOnet telescope located in somewhere in Europe. Spain is actually a very nice country for that because of the nice weather. But that is one site that we would like to support. If you can give us some ideas or volunteer or whatever, I think that would be great.
Great. Okay, thank you. Somewhat related question. We had one from Massimo Uberti, who just asked for confirmation. You can use AAVSOnet even if you live in Italy, right?
Oh yeah. I mean, it's all on the network, on the internet, so it doesn't make any difference where you're located.
Sweet. Okay. So now 2 questions about the proposal requesting process. First one comes from Ray Tomlin, who asks if there's any way to see where an accepted proposal has been slotted into the schedule.
Slotted into the schedule? No. And the reason is that it uses ACP and ACP's expert scheduler, and it optimizes the observing time through computer analysis. And so you really don't know when that observation is going to take place. It could be tonight, it could be tomorrow night, it could be early evening or late evening, however it works out that it is most favorable for that observation. Saying that, if you have something where you need specific timing, so you say you have an eclipse coming up or something like that, if you can tell us what times you want the observations to take place, then we actually can schedule it for that particular time interval. So there are ways in which you can hard code it and make sure that it is done when you need to. But as for just a generic observation, no. What happens is that you'll get an email that says, you've got data. And so then you know at least that your observation has been taken.
Okay, great. And follow-on question to that. This one comes from Chris Mahar. Once you have requested an observation and your proposal's been approved, how long is it typically until you get your data back?
It depends. The usual schedule is it takes probably a week to go through the proposal allocation committee and get scheduled onto the telescope or something like that. And then it just depends on weather after that. It may come down the next day, it may come down a week later. It's just hard to say exactly when it's going to be taken. But it's not something where it's instant turnaround. You submit a proposal and that night something is observed for you. It's very rare unless there's a specific reason for doing it and you highlight it in your proposal saying, I gotta have my data now. Then we actually will give you priority and try to get through the process quicker.
Great, okay. Thank you. I think we have time for one more question. This one comes from Margaret Miller, who asks, what is your background, Arne?
My background, oh my gosh. I'm a professional astronomer, retired. And I worked at Goddard Space Flight Center and Ohio State University and the U.S. Naval Observatory, and then was director at the AAVSO and things like that. So I basically moved around and mostly as a research astronomer. So more in the lines of instrumentation and doing observation than anything else.
Extremely impressive. Thank you. Okay. I believe that's all the time that we have for questions. I did see one question sneak in at the last second, which if you want to answer, Arne, you can do so in the Q&A box by typing an answer. No obligation on you, though.
Okay.
All right. Thank you so much. Really appreciate it. Next, we will go to Eric Hintz, who is the current leader of the short period pulsator section. Eric, take it away.
Okay, Lauren, warn me if my slides come up wrong.
Will do.
Okay, does that come up
Okay.
right, Lauren?
No, we're seeing the presenter view. So if you could swap the displays.
I'll swap them again. I don't know why I did that.
Thank you. Looks great.
There we go. Okay, I realized I should probably have started a little bit with explaining short period pulsators. Not assuming everybody knew what they were. I've been working on them for 35 years, so they're kind of second nature to me. But the short period pulsators are stars that are literally changing size and temperature in a very periodic fashion, so repeating over and over and over again. Some we've watched for over 100 years now, ranging on periods from seconds, hours, days, up to months. So the term short period pulsator is a very relative term in that sense. One of the early things that were very close to the AAVSO work in actually the same place was the discovery of the period luminosity relation for Cepheid variables, where the time it takes the star to go through a cycle, go from brightest through faint back to bright, is related to how absolutely bright the star is. So it basically gives you the wattage of the light bulb for the star. And that allows us to then, if we see a star like that at a distance, we can figure out how far away it is. And then this was used to build up the nearby galaxies, find how close M31 was and the other nearby objects. So this was a very powerful tool early on. And one of the things that came out of this, as people kept scaling the universe, was from Hubble's work, was basically a constant called H0, so the Hubble constant. And that was great for a very long time. We got it settled down to a reasonable value. We started out with 50 and 100, settled into the 70 range, 75 range, and we thought we had it. And everything was good. But something's come up called the Hubble tension. And some of this has led us to question some of our understanding of all the pieces that make up the distance ladder that allow us to scale the universe. And so if we look at one kind of view of the Hubble tension, we start with the geometry. So we start with parallax for the closest stars. And from those, which there's really no way to argue with the parallax. And then you'll notice we go to two sets here. To the right-hand side, we go over to classical Cepheids in the Milky Way to start scaling the universe. To the left, we might go through the faster pulsating RLR stars. And then we find those in local group galaxies and start scaling. And then we go through a number of other distance indicators. The tip of the red giant branch is used now. Then type 1a supernovas, so where the accelerating universe came from. And from that track all the way to the left, we get a very nice value of 73.2 for the Hubble constant with fairly small error bars. If we come slightly to the other side and use surface brightness fluctuations on distant galaxies, 73.3, pretty good agreement. We come over through the classical Cepheids and then through the local group of Cepheids and galaxies, then the type 1a supernovas, 73.0, all with small error bars. It looks like we have a beautiful solution. Well, if we go this is working from the Earth outward through the nearest stars to the next nearest to the galaxies and then working our way through scaling the whole universe. Well, if we look the other way, there's missions out there that look at the cosmic microwave background and then use theory to come back towards the Earth. And from their work, they get a value of 67.4 with small error bars. The error bars for these values from the distance ladders, starting with pulsating variable stars, the H0 for those, the error bars do not overlap with the cosmic microwave background. This leads to the term Hubble tension. Which one is correct? Where is the error bar? And one of the things that can happen from that is looking at maybe there's something about the Cepheids or the RLRs, both short period pulsators. Maybe we don't understand them as well as we should. Maybe there's subclasses, things we should eliminate from the period luminosity relation. And so work has been going into taking another look at the Cepheids, classical here and type 2, and then also the RLRs. And that's where there might be some need for some help in terms of people monitoring some of these Cepheids that maybe we've let slide. We've thought maybe we understand the RLRs and the Cepheids so well we don't need to keep observing them. Well, one of the places we can go to kind of get some new information on the Cepheids is sliding over into the infrared spectral range. The left-hand figure here is actually a Delta Scuti, which is my normal happy objects to study, but have been doing a lot more Cepheid work. On the left-hand side, so what you're seeing here, you kind of see an area with lines in it, then a gap, another area, a gap. So in the infrared, we lose part of from ground base, we lose regions because of the Earth's atmosphere and mostly from water vapor. And so we have a region here, which is about all the way on the left is the Y filter, then the J, then the H, and then all the way down in the bottom right is the K filter. So you might have heard of those, and some people have configurations for being able to observe in these band passes. The deep spectral lines you're seeing in the first two regions on the left are Paschen lines. So normally we deal with H alpha from the Balmer sequence, but these are the Paschen lines. And then in the middle set, in the H filter, you're seeing the bracket lines. So there's a lot of interesting information in here. And if we come to the right-hand side, this is actually a Cepheid, and a spectra for when it's hotter is the top one, and a spectra when it's cooler from its pulsation cycle at the bottom. And down at the very, very bottom here, we're seeing carbon monoxide bands, which when I first saw carbon monoxide in a star I never thought would have carbon monoxide in it was kind of shocking. And those are some things that can impact some of the studies that have previously been done on Cepheids. Well, this infrared work is nice. We'd like to put it into context of the classical measurements of these objects in the optical band passes. So if we come here on the left-hand side, these are three different observations, three different dates on a Cepheid called CP-CEP, and these are the carbon monoxide bands. And you can see the different depths over the pulsation cycle. So if I come over to the right-hand side, you can see where each of these fell along this is the Assassin V data. See the green and the orange are kind of along this flat, and the purple is on the rising edge where the star is getting hotter, and we're starting to lose the CO. And we have the test band. But it would be nice if we could put these in full context by having people observe in all the different band passes, UBVRI filters, gun filters, all the different ones, so that we can put the infrared observations at the right phase and make sense of what's going on with these objects. So that is kind of a plug for us to keep looking at the pulsating variables, even though we thought maybe we understood them. The Hubble tension is sending us back to say, maybe there's some things we need to learn here. And so that's the invitation, is for you, for observers out there, northern, southern hemisphere, there's Cepheids every direction you look, joining in, providing light curves. And a lot of these are one or two observations a night on a given target, and then night after night after night of observing. So hopefully we'll get something exciting for people to join in on, and have some fun with these kind of my favorite objects out there, pulsating variables. And with that, I'll stop screen sharing and turn it back to Lauren.
Great talk. Thank you, Eric.
Yep.
All right. So next we will be hearing from Walt Cooney, who is currently the leader of the Cataclysmic Variables Observing Section. Walt, please take it away.
Thanks, Lauren. Let me share the screen here. Okay, you should see the slides, and now in presentation mode.
Yep, looks good.
Okay, fantastic. Well, thanks. My background is actually chemical engineering. I am retired, and my hobby since I was a little kid, I did a book report on the constellation that I thought was called Orion. I've been doing this since then. I finally figured out it's Orion. And co-leader for the CV section is Sean Dvorak. And let me tell you a little bit about what cataclysmic variables are. They are variables that explode. They do exciting things. They definitely are things you can watch happen in the universe. Well-known supernovae and novae are cataclysmic variables, but there's lots of other kinds. There are things called dwarf novae, recurrent novae, polars, intermediate polars, Z-cams, nova-like variables, and the list even keeps on going from there. And so this is a close-up of cataclysmic variable, artist rendition, of course. And with the lone exception of type 2 supernovae, cataclysmic variables are actually binary stars. And I don't know if you can see my mouse, but they have a semi-normal star that's a donor star that rotates in tandem with a white dwarf. And material from the donor star flows down into an accretion disk, which then spirals into the white dwarf. And so that's the physical system. And quite a few things happen in these semi-stable-ish systems, you know, novae, supernovae, etc. And to talk about just a couple of them in particular, classical novae, a regular nova, a classical nova, a nova, all the same thing, slightly different terms. They'll rise in brightness anywhere from 7 to 15 magnitudes. And in this case, what's physically happening is the hydrogen from the donor star circles down through the accretion disk and then builds a hydrogen layer at the white dwarf. And at some point, that hydrogen layer is dense enough and hot enough that it goes nuclear, and we have fusion, and we have a nova eruption. And the hydrogen is ejected away from the star. Of course, some of it burns as well. A lot of it is just ejected, as well as some of the underlying white dwarf that was below that layer of hydrogen. And on average, just in our galaxy, we have about 10 of those in a year, although it varies quite a bit, anywhere from maybe 5 to 20 would be typical, at least the ones that we see happening. And here's an example of one. Nova Cygni 1975 got up to, I think, 2nd magnitude. And this is it in not too far from the North American Nebula back in 1975. And so here's Nova Cygni 1975 then and now. And so I'm showing you here a little bit about what happened, what we saw happen, and back in 1975, and what we're actually seeing now. It's still interesting to us. This is the light curve. This is just data on the brightness of that nova that was submitted to the AAVSO. And so here's where it went off in 1975. We managed to catch it before it hit peak. It peaked at around 2nd magnitude. And then over the course of some months, it faded first quickly and then more slowly over time. And it's still fading. If you notice, so this is October of 1975, it had gone down from 2nd magnitude already down to about 8th magnitude. Well, this is current data below, pretty current. This is 2 years ago. And it's running between 18 and 19 right now, pretty faint. And it's still busy doing things. And that's another reason why we're so interested in these objects is they continue to do things based on the interesting physics they have going on that we're trying to better understand. And so this is data for 3 different nights. And actually, this was data that I took with one of the AAVSOnet telescopes. This was from the Madrona Peak telescope out in the hill country of Texas. and you can see the star moving back and forth between about 18.4 and 19.4, give or take. So it's moving a whole magnitude just over the course of a few hours as we were watching the star. Another kind of cataclysmic variable that's getting an awful lot of press nowadays, and for good reason, are recurrent novae. And so these are novae just like 1975, except that we've seen them go nova more than once. And so we only know of 10 of these so far in our galaxy, but there's certainly more. And we only know of those 10 because we've only been watching for our short little span of time. And those are all we have picked up so far. The one, of course, that's getting the most excitement is T Corbor, T Corona Borealis, and it is predicted to go off any day. And last went off in 1946, and it's predicted to peak at around second magnitude. And let me tell you why we think that's true. And I'll admit that this top slide I stole from Dr. Brad Schaefer, who is actually on the call this afternoon. Thanks for being here, Dr. Schaefer. I hope you'll be able to answer some of the questions that maybe I won't be able to. But anyhow, so this is his slide from a presentation he gave to the AAVSO last September. And it shows the 1946 eruption and some really interesting behavior of the star system before it went nova. And so the green is visual or eyeball light curve, effectively. Blue is with a blue filter. And so what we're seeing now mimics that behavior of pre-1946. And as a matter of fact, this slide, of course, it's last September, so it's a little dated. If you look and see, we have a big drop in the blue and V bands right before it finally did go up. And so this is the current data. I pulled this off the AAVSO website yesterday. And so it's spread out from, well, really, I guess about September last year. And so you can see we have gone into the up phase because the B and the V have both risen. We've got these modulations that are a different kind of modulation. Most of it is an ellipsoidal variation in light because the stars the one star is kind of a teardrop shape. But now what we see happening too is the B and the V have both trended down. And so we're seeing this that we weren't seeing yet previously. And so it's pretty clear it's about to go. And as far as when, I think the answer is any day now, or certainly I would hope in the next few months. You can't always say it's going to do exactly what it did last time, but it would certainly be a good bet that it'll be very similar. Okay, let's switch over to another kind of a cataclysmic variable to give you another flavor. These are a favorite of mine. These are what are called intermediate polars. And so here is an artist's rendition over here. You've got the donor star, you've got the white dwarf, you've got the accretion disk, but this white dwarf has an incredible magnetic field. And that magnetic field is so strong that before the material fully cycles down into the white dwarf, the magnetic field grabs it off of the accretion disk and pulls it down into the white dwarf via the north and south magnetic poles. These are really fascinating physically. Active area of research, a lot we don't understand. One of the classic ones is called DQ Hercules, and I pulled some AAVSO data for that. And you can see it typically runs 14 and a half, but then it drops to 17. And so I have blown that up a little bit with a couple of data sets here. And you can see these beautiful eclipses where this system is actually oriented kind of line of sight to us. And so every about 4 2/3 hours, the white dwarf and much, if not all, of the accretion disk are blocked out of view behind the donor star. And so really great data here. So, and then one last thing I have to mention too, because these are so interesting. These are called Z-cams after Z camelopardalis. And these are what are called dwarf novaes. And it will typically bounce around between, say, 14th magnitude and maybe as high as 10th magnitude. And you'll notice here that the visual data points, which are the black circles, and the photometric data points, which are the green squares, really line up beautifully. So this shows nicely how both visual and photometric photometry with a CCD or CMOS camera complement each other. But what's so interesting about these Z-cams is they bounce back and forth as they brighten and fade. And then on their way down, at some point, they get stuck. And in this case, this one hummed along at about 11.5 for, well, let's see, I guess that's about 6 months in this case. And then it started back on its way down, went back to bouncing back and forth, and then it decided to get stuck again. And so there's a lot to understand about this. How long it bounces versus how long it gets stuck is unclear, and it varies quite a bit. And so it's our watching it that helps us figure out what's going on. Okay, so current research. What are the kinds of things that our work following these stars can help? Well, there's a lot still uncertain. How do cataclysmic variables get to someday be a type 1a supernova, which were the ones that Eric talked about in the cosmic ladder for distances? The evolution of these things. There are lots of different flavors, dwarf novae, novae-like, etc. But really, are those just snapshots of the same kind of system that's moving through an evolution? And these are snapshots of where the system is at different times in that evolution. We don't know. We have some evidence that this is the case, at least between some types of cataclysmic variables, but fleshing that out is a lot of work to do there. Are all novae recurrent? We don't really know. The answer might be yes, or maybe the answer is most of them, and we just haven't been around long enough to find out if it's true or not. Lots of other things I won't spend any time on, but just to mention, there's other physics that do things like negative superhumps, period gaps, period bouncing, flickering, and the variable star light that we measure. Lots of interesting things going on. And then cataclysmic variables are laboratories for accretion disk physics. Generally, a lot of things happen with cataclysmic variables that are on relatively short time scales that we can study. And so it helps us understand what's going on then for longer term things that we can't study so easily. And so that includes things like black hole accretion disks and planetary formation. One of the things that's been discussed is, hey, do the pros need our help? Do they use this data? And so here's at least a little bit of info on that. These are alert notices that have come out in the last year where professional astronomers have asked for AAVSO help monitoring or doing some particular work on various cataclysmic variables. I'll point out in particular, it's not uncommon if you notice alert notice 838, where we are following 11 dwarf novae in support of HST observations last year and this year. And that's because the Hubble Space Telescope uses an ultraviolet spectrometer that can be damaged if the star is too bright. when it's observed. And so for cataclysmic variables, the professionals specifically want to use that instrument, but we have to make sure the variable star is at the low state, low magnitude, so that we don't damage the instrument on Hubble. And the folks at Hubble actually need a go, no go based on light curve information within 24 hours in order to approve that the observation actually takes place as scheduled with Hubble. So the AAVSO participates in that quite a bit. So our section, we have regular section meetings. Recent speakers have been Dr. John Thorstensen of Dartmouth and Dr. Enrique de Miguel from Spain. Our next meeting is going to be July the 21st, 2 o'clock Eastern. And our speaker will be Dr. Josh Hintz. And he is actually a nuclear physicist by trade. He has a telescope in the Atacama Desert in Chile that he runs remotely and produces a huge amount of data, mostly on the cataclysmic variables. And he's going to talk to us a little bit about our system Sunday, July 21st. Everyone's invited. If you go to the CB forum, there's information there on how to get the link to the website or to the Zoom meeting sent to you. And that's it for me. And I guess I'll just summarize and say we need your help. There is way more work to do than we could possibly have enough people for. So we would definitely appreciate your help. Thank you.
Excellent talk. Thank you so much, Walt. Okay, so I see that we've had quite a few questions come in for your talk and for Eric's. I think we'll start off with this one directed at Eric really quick. So Eric, Tasso Napoleano has asked if the short period pulsator section is involved in researching specific period luminosity relations for any types of pulsating stars other than Cepheids, for example, high-amplitude Delta Scutis or SX Phonesis stars.
Yeah, it's basically the entire instability strip that we're going to chase. So from the Cepheids at the top down to the Delta Scutis at the bottom. If people observing techniques can get into the second range, then there could be some work that people could do would contribute on white dwarfs and the pulsations down there, because that just continues the instability strip down. But that's, yeah, it's the whole instability strip and the period luminosities, particularly the Cepheids and then the Delta Scutis.
Okay, cool, thanks. All right, next up, we have, this will probably not come as a surprise, but we have quite a few questions on the topic of T Corona Borealis. So, Walt, James Schweitzer would like to know, what is the easiest and quickest way to be alerted that someone has spotted T Corona Borealis brightening?
Yeah, that's a question. Lauren, maybe you can help me with that. The way I do it is I check the AAVSO every day, looking at T-Corbor's most recent data, which is, just a couple of clicks. If I'm not mistaken, though, there is an alert notice also set up by the AAVSO. Is that right?
Yes, that is correct. We have a alert notice which was sent out, and we also have a dedicated forum thread, which here, I'll share my screen real quick so that you guys can see the forum thread. It would be this window. Yep. Okay, so when you go to our website, go up to the community tab, click on forums. There is a time-sensitive alerts forum right here. We have pinned to the top this T Corona Borealis time-sensitive alerts forum thread. Whenever someone who has read the alert notice detects T Corona Borealis brightening, they are instructed to post to this forum thread. So if you go into the AAVSO forums, logged into your AAVSO account, and you subscribe to this thread, it will send you an email as soon as someone thinks that they have seen T Corona Borealis brightening, because they'll post here and it'll automatically be emailed to your account. And this has happened once or twice before where there were false alarms due to instrumental issues. So, you know, you might get a stray email or two over the course of months, but you will get an email when T-Core actually does go up. So this is what I would recommend. If you want to know immediately, as soon as a detection has been made, do this.
Thanks, Lauren.
Sure. Okay, so our next question on the topic of T-Core vaguely, recurrent novae in particular, comes from Max Delaney, who asks about how much of the original white dwarf's matter is ejected when it goes nova, or looking at things from a different perspective, how many times can a nova recur before there's nothing left to go nova?
Yeah, that's a really good question. I don't have an exact answer other than to say that it's a fairly small amount. It is, and there's several professionals on the call. Actually, maybe they could put something in chat, but I think it's on the order of a few percent of the mass. And as far as it exhausting the star, I don't know that that's what's going to happen. It actually is a really tough question that gets into the point about how do you get to a type 1a supernova. A type 1a supernova is when the white dwarf has reached the Chandrasekhar mass limit of about 1.4 solar masses. And so the original idea is that all this material that builds down onto the white dwarf slowly increases the mass until it reaches that limit. And then we have a type 1a supernova and it blows itself to bits. The tough part is then we found out that, well, as you have intermediate nova stages, if you do have those before you go supernova, star gets smaller after the white dwarf goes down in mass rather than up in mass at each explosion. And so I guess that's a fancy way of saying I'm going to punt on that question.
It's an educational punt.
Yeah, thanks. Like I say, maybe, I mean, Paula Scoti and Brad Schaefer are both cataclysmic variable expert astronomers on the thing. Maybe they could add to that. And I think they can only do it via chat the way this is set up, unfortunately. So
I believe so, yeah. Okay, thank you. I'll keep an eye on the chat in case one of them decides to chime in. So our next submission about T. Borealis is actually a quick comment, which I'm going to share because it sounds like it could be generally useful. Gregory Shanos has mentioned that an easy way to locate T. Borealis when you're using a GO2 telescope, and I'll add, this is especially relevant to users of the C-star since you aren't able to type in custom coordinates, is to set the telescope to find the galaxy IC4587 because T. Borealis is right next door to that. So thank you for that tip, Gregory. All right. Our next question here is addressed to Eric. Eric, Margaret Muller would like to know how someone who has very little experience with variable stars can learn what they need to know in order to make useful observations of short period pulsating stars.
That is something we're trying to do a better job with in the short period pulsator section. Horace Smith has been doing a monthly newsletter for the section. And probably one of the best things we could do in there would be to provide that initial basic information of what observations we need, what kind of rate we need on them for the all up and down the instability strip, what researchers would like to see. And so I might suggest that to Horace for next month's newsletter. It'd probably be the best place to start.
Yeah, good idea. As the person who has been posting the newsletters, I can chime in and testify that they are quite informative. So check them out.
Can I add to that too, that if part of that question is about just learning how to do variable star photometry, that kind of thing, either visual or CCD/CMOS, there are lots of really good references that we put up on the AAVSO website, including a manual that's really helpful. And we also have, I guess, 30 or 40 various AAVSO members who serve as mentors. And you just need to ask for one, and we'll see if we can't set you up with somebody who can help out.
Great point. Yeah. Thanks, Walt. In fact, if neither of you mind, perhaps I can screen share real quick to show where you can find those resources on our website. Okay. So going back to the AAVSO homepage, let me move the Zoom toolbar out of the way. It's overlapping our AAVSO toolbar. All right. It's just up here in the Getting Started tab when you visit aavso.org. We have both a tutorial section with a tutorial for just the very basics of variable star observing. We also have our observing manuals, which Walt mentioned. So thank you for bringing those up, Walt. Those are invaluable resources for people who are just starting out. Okay. So next up, we have a couple of comments. One was on the topic of T-core bore and getting an alert for that. Wayne Buck has pointed out that it's likely that the Astronomer's Telegram service will publish a notice once T-core bore goes up. I think that is a very fair point, although I don't know what the typical delay is on that. And we also have someone asking for a repeat of the instructions on locating T-core bore. For this one, I'm actually going to direct you to the Q&A box in Zoom where you can see the comment, which was submitted earlier by Gregory Shanos, who said, locate the galaxy IC 4587 is one way to do that. I'll put that in the chat. All right, and going back to the question which was addressed to Walt about mass loss and cataclysmic variables. I see that Paula Scody and Brad Schaefer have both chimed in at this point in the chat. So, Walt, would you like to read out what they said, or?
Okay, sure. Yeah, I'll learn something. Yes, from Paula. Yes, it's an ongoing debate as to whether the white dwarf gains or loses mass after a nova event. The mass loss can be up to 8% in the nova, I think, but often less. And then Brad goes on to say, Walt got it right. So I like that part of this comment. The mass ejection is largely unknown, with the mass ejected being crudely comparable to the mass accreted since the last eruption. As he says, whether the white dwarf is gaining or losing mass over time is part of the uber important type 1a supernova progenitor problem, with T-core bore being a poster child for a whole class of progenitor models. Your T-core bore question is at the excitation front line.
All right, cool. Thank you to both Paula and to Brad for chiming in on that. We appreciate your input. Okay, now we have another question directed to Walt. This is actually coming from one of our viewers on Facebook. Why is it that so many observers do not transform their reported magnitudes, especially, using T-core bore as an example? We're getting hundreds of measurements, but few of them are transformed. Does the transformation matter when you're observing targets like this, or is it really just a matter of we're looking for when it goes into outburst?
Yeah, great question. A couple of different pieces to that. Transformation is important. One of the struggles with a massive effort amongst thousands of people all over the globe with different equipment is trying to make the data as consistent as possible across that group and reduce the scatter. And transforming your star estimates would be hugely helpful and is highly recommended by the AAVSO. I will say in the past, that was pretty hard to do. You probably had to develop your own spreadsheet to do all that work. It was a lot of work. Nowadays, that's changed tremendously. The AAVSO photometry tool that is online now has transformation capability, and it's really simplified that effort a lot, and I do it now. And I didn't used to do it in the spreadsheet days. It was too much work, and I never developed my own spreadsheet. And it does require that you figure out the transformation coefficients for your particular system. And so that generally means you shoot pictures of a standard cluster like M67 or NGC 7791 in Cassiopeia to figure out what your color effects of your system are. And then you can do that transformation pretty easily. And for those who aren't familiar with transformation, it's basically taking the fact that everybody's system is a little different and the colors are measured just a little different and trying to put them all together so that they're on the same standard system. Now, I will say, though, that the data is still useful if you don't do it. We can still get periodicity. We can still average the data over many observers, et cetera, et cetera. But it is certainly better data if you do transform as well. And I hope that pretty much answers the question.
I think it does. Great answer. Thank you. And I feel like I should mention that just last month, the last webinar before we started this mini series was presented by Dr. Brian Kloppenberg, our executive director, and he detailed how you tackle the concept of transformation and gave some pointers on resources to learn how to do transformation. So for those of you out there who are interested in it, go to our YouTube channel and it'll be one of the most recent webinars that we've shared. Okay, another question for Walt. This one comes from John Fisher. How does an outburst, a nova outburst, affect the spectroscopic profile of a white dwarf in a cataclysmic variable? What are the changes comparing before and after?
Well, as someone who hasn't done much spectroscopy and doesn't know a whole lot about the details of that, I will definitely have to punt on that one. I'm sorry.
Okay.
Again, maybe Brad or Paula would have the chance to say something in the chat if they wouldn't mind.
Okay. All right. I can say from the limited amount of spectroscopic work that I've done on novae, which is not studying the novae directly, but rather reviewing the spectra which people submit to the AAVSO of novae. The spectrum at quiescence seems to often be dominated by the red giant. You don't see the white dwarf a whole lot unless you're looking at the blue end, and then you can see everything is generally in absorption. You might have some weak Balmer emission. During the outburst, all that goes out the window and you get an extremely bright thermal continuum that's very blue, and you get some large emission lines. But other than those general terms, I can't share the details. So if Paula or Brad would like to weigh in, that would be very nice. All right. Now, it looks like we're just about out of questions. So while we wait for just a second in case there is some spectroscopic input to be had, I saw that we had a question earlier about how do you join a section. So I'm going to go ahead and recap that a little bit. So if you have been hooked by any of today's presentations and you just have to get involved, which I would not blame you for that, the way that you can get involved with these sections is by reaching out directly to the people who you've just heard from, the section leaders. To do so, if you'll allow me to share my screen very quickly. Let's juggle that tab over here. Okay, so from our homepage, if you scroll down, you come to this tic-tac-toe grid of options. This over here that says observing sections, click on that, and you'll be brought to our observing section list. Choose the one that you're interested in. For instance, I'm seriously considering joining the Cataclysmic Variables section right now. Click on that section, and right up here at the top, you'll see the section leaders with contact links. If you are logged in to your AAVSO account, which I'm not currently, but I could do quickly, you click on a contact link and you'll have the option to send that person an email. Do so. Reach out to these people, let them know that you're interested in becoming involved, and they will help you to get started in this section. Also, if you want to become more involved just in the sections community and kind of keep up to date with what's going on, Each section has, and it's linked from the sidebar on their webpage, each section has their own dedicated forum on our website. So if you are, again, if you are logged in, then you will be able to subscribe to it, and you can view it even if you're not logged in. And yeah, it's a good place to keep up with what's going on in the section. So those are my 2 bits of advice. The primary being just reach out to these people and we will help you get involved. All right, I see that we had a comment on Nova Spectra from Paula Scody. Walt, would you like to read that out?
Sure. Paula says the spectrum changes dramatically. At first, the spectra are from the envelope, from the ejection. Then it's all broad emission at high velocities. And that changes then into low density emission. Very complicated with many papers in the journals about the changes. See Bob Williams' spectral papers for one. So thanks, Paula, and thanks, Brad, for being the folks who have the deep knowledge of this and for coming. Thank you.
Yes, thank you. All right, and I believe that brings us to the end of our question and answer period. So let me go ahead and get up our closing slides. There we go. All right. First, I would like to extend a heartfelt thank you to Walt Cooney, to Eric Hintz, and to Arne Henden for sharing their time, knowledge, and expertise with us today. Thank you, guys. We really appreciate everything that you do. I would also like to extend a thank you to our 2024 series sponsor, Voice Astro. And in just one moment, I will be pulling up their sponsor statement so that I can read that out, but it will take me a second. It's inconvenient when you have your notes on a digital device and then that digital device crashes. Okay, there we go. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. And I promise their webpage will not crash like my phone just did. All right, as a reminder, today's webinar was part of a mini series which we're running all throughout this month. Next week, we'll be hearing from the spectroscopy section, the high energy network section, and the photoelectric photometry section. So if you're interested in any of these topics or think you might become interested in any of these topics, I really hope that you will join us in that special webinar. To learn more about the plan for the webinar or to go ahead and register, please visit our webpage at aavso.org/webinars. Hope to see you there. All right. Special announcement about our upcoming 113th annual meeting. It will be located at the U.S. Space and Rocket Center, and I'm pleased to see that this image loaded this time. It's one of the coolest places on this planet and the perfect setting for our several days of scientific talks, poster session, and a Arlo Landolt lecture, a special keynote on T. Corona Borealis presented by Dr. Brad Schaefer, who of course is here in attendance and has been helping us with answering cataclysmic variable questions. I can't wait to hear his presentation. The meeting will take place in early November, and you can find more details about various registration deadlines, talk abstract submission, and more stuff about the venue if you visit our webpage at aavso.org/113. Last but not least, I would like to thank everyone who joined in during today's webinar. All of you out there in the audience, it's your participation in all of our programs that allows us to keep growing, keep educating, and keep making an impact on variable star science. So thank you, all of you. We're so grateful for your support. Today's broadcast has been recorded, and if you would like to go back and reference the recording, you are in luck. You can find it on our Facebook page, where it will be automatically uploaded just as soon as I click the end webinar button here. You can also find it within a few days on our YouTube channel, where it will be added to a growing archive of probably at this point over 100 educational webinars. It's covering all sorts of topics, including many past presentations on cataclysmic variables, such as Paula Scoti's recent excellent overview of the field of cataclysmic variables, or past presentations on the Hubble tension in depth, following up on what Eric said. It's a great resource, so check it out. To find our library on YouTube, just visit the YouTube website and search for AAVSO HQ. That's our username. When you log out of today's webinar, you should be automatically redirected to a survey, and I would really appreciate it if you could please fill it out. Let us know what you thought of today's webinar and what you might like to see us do differently next time. I'm looking forward to reading your feedback. Okay, I think that brings us to the end of our closing announcements. So I'd just like to say one more time, a heartfelt thank you to Walt, to Eric, and to Arne from all of us here at the AAVSO. We appreciate you and everything that you do with your sections. Thank you. And with that, see you all next time.